Hello and welcome dear students. Today we will be discussing about the topic groundwater recharge and discharge processes. In this lecture, we will discuss about the basic concepts of groundwater and recharge and discharge processes. Let us discuss them in detail. Aquifer. An aquifer is essentially a subsurface layer of rock or sediment that is saturated with water and is permeable enough to transmit significant quantities of water to valleys and springs. For a geological formation to be classified as an aquifer, it must have a porosity to hold water and the ability to allow water to move through it easily through the connected pores, which is called permeability. Common geological materials that make up aquifers include unconsolidated sands and gravels, permeable sedimentary rocks like sandstone and limestone, and heavily fractured volcanic or crystalline rocks. There are three main types of aquifers, which are unconfined, confined, and perched. So far as unconfined aquifers are concerned, these aquifers usually closest to the ground surface. The top boundary is the water table, which is simply the level where the ground becomes fully saturated with water. Here the groundwater pressure is approximately as there is no waterproof layer above it. These aquifers can be recharged directly by infiltrating rain or snowmelt. So far as confined aquifers are concerned, now imagine a sandwich where the aquifer, sand or rock, is trapped between two layers of materials that water cannot easily pass through, like thick clay or solid rock. This is a confined aquifer. The aquifer is confined or sandwiched between impermeable layers, often called aquitoids or confined layers, both above and below it, because the water is trapped and often enters the system from a higher elevation elsewhere. It is under pressure. If you drill a well into a confined aquifer, the pressure will push the water up the well pipe to a level higher than the actual top of the aquifer. And the important aquifer is the perched aquifer. Sometimes as water is soaking down from the surface towards the main water table, it hits a small isolated patch of clay or rock that it cannot flow through. The water pools on top of this patch, creating a small separation zone of saturation. This is called perched aquifer. It sits perched above the main water table, separated by an unsaturated zone, that is the dry soil or rock. These are often small and not laterally continuous. They might dry up quickly if they do not receive regular recharges. Now let us discuss about the groundwater sources. There are specific mechanisms and pathways by which nature replenishes the subsurface water supply. We can categorize these natural sources into three main groups: direct precipitation, surface water bodies, and subsurface leakage. So far as the precipitation is concerned, while we can discuss about rain and snow, the most direct source of recharge is precipitation. This includes infiltrating rainfall and snow melt. Infiltration is the process by which water on the ground surface enters the soil. However, infiltrating water is not yet recharged. It must pass through unsaturated zone and actually reach the water table to become a recharge. So far as the surface water bodies are concerned, where we have to basically discuss about rivers and lakes. The losing stream, if the water level in a river or lake is higher than the water table in the ground next to it, water will leak out of the river through the riverbed and down into the aquifer. We call this a losing stream or sometimes an influent stream. Similarly, lakes can act as a recharge source. If the lake level is higher than the surrounding water table, water seeps out of the lake, becomes bottom into the ground. So far as the depressions, which are focused recharges, nature is rarely perfectly flat. In terrain that is hummocky, bumpy with small hills and hollows, rain does not soak in evenly. It runs off the bumps and collects in the hollow or temporary ponds. By collecting in these small depressions, the water is concentrated in one spot. This creates a stronger downward push and allows water to soak in deep enough to escape evaporation and plant roots. Even if the surrounding higher ground is dry, these puddles act as localized injection points for recharge. So, if we discuss about mountain block recharge, in valley aquifers, water often enters the system via fractures, colluvium, talus in the bedrock of the surrounding mountains is known as the mountain block recharge. The mountain front recharge occurs when water flows off the mountains as surface runoff and infiltrates the ground at front, where the mountains meet the valley floor. As these streams flow across the permeable alluvial fens at the edge of the basin, they lose water into the ground, becoming losing streams. This water soaks in at the proximal end, that is at the top of the fen, to recharge the aquifer. Now, if we have to ask what is groundwater recharge, to understand recharge, we must understand what is not a simple event. In hydrogeology, we distinguish between the water entering the ground and its subsequent movement into the infiltration. Infiltration is the process of water entering the subsurface from the surface. Percolation is the movement of that water through the soil, sediment and rock after it has infiltrated. Think of percolation as the downward journey of water under the influence of gravity. As the water percolates down through the unsaturated zone, that is the area above the water table where pores contain both air and water, it travels vertically. This journey continues until one of these two happens. First is groundwater recharge, which is process by which water moves downward from the surface of the earth to enter the saturated zone of an aquifer, and second is the interflow, which occurs when the percolating water encounters a layer of low permeable material like clay that slows down its vertical progress. So, this forces the water to move sideways or laterally, a process we can call interflow. To understand the recharge, we must understand the difference between the potential recharge and the actual recharge. Let us first discuss about the potential recharge. Potential recharge is the amount of water that successfully crosses the soil zones. It is the water that drains vertically downward from the base of the soil layer after the demands of the evaporation and plant transpiration have been met and the soil has reached field capacity. Field capacity is the amount of water that remains in the soil after it has been thoroughly soaked and allowed to drain freely. It represents the maximum moisture levels in the soil that can hold against the pull of the gravity before an extra water flows downward. Once this limit is reached, any additional water drains away to become a groundwater recharge. The second is the actual recharge. Actual recharge is the amount of water that actually reaches the saturated zone, that is the main aquifer. Now, let us discuss about the groundwater recharge mechanisms. The process of recharge begins with the precipitation. that is rain or melting snow. When water hits the land surface, it attempts to soak into the ground. This process is called infiltration. However, not all rain infiltrates. The soil has a specific infiltration capacity, which is the maximum rate at which it can absorb water. For example, when the soil is dry, it acts like a thirsty sponge. Capillary forces help pull the water in, so infiltration is fast. As the soil gets wetter, it cannot absorb water as quickly, so the rate drops until it reaches a steady equilibrium rate. If the precipitation falls faster than the soil can absorb it, the excess water pools on the surface, that is the depression storage, or flows over the land surface as runoff and ends up into the streams, never entering the subsurface. Once water infiltrates the surface, it enters the soil zone. This is the most critical step in the recharge process. We can visualize this using the soil moisture balance concept. Consider the soil as an analogous to a sponge, capable of retaining a specific quantity of water against gravitational forces. This maximum water retention capacity without any water loss through dripping is termed field capacity. During the summer months, elevated temperatures and increased plant water requirements lead to the desiccation of the soil, resulting in what refers to as a soil moisture deficit. Prior to any water percolating down to the aquifer, precipitation must first replenish this deficit efficiently, rehydrating the sponge while water resides within the soil. Processes such as plant transpiration and evaporation occur concurrently, collectively known as the evapotranspiration. So, the rule of recharge is that it generally only happens when the soil is wet enough, that is at the field capacity, to overcome the suction of the dry soil and plant water demand. Any excess water then drains downward. Once the water escapes the soil zone, it begins a downward journey through the unsaturated zone, which is also called the vadose zone. This zone is particularly filled with air and partially filled with water. So, the water moves vertically downward under the influence of gravity. This movement is called percolation. The speed of this movement depends on the moisture content of this media. As the moisture content increases, the permeability increases. The water often moves as a front or a pulse, similar to how a wave moves through the ocean. This process results in the delay, as it may require days, months, or even years for a particular rainfall event to traverse a thick unsaturated zone. Eventually, the percolating water reaches the capillary fringe, a moist zone situated just above the water table, where water is drawn upward by surface tension upon crossing from the unsaturated zone into the saturated zone. So, the water becomes recharged, leading to a rise in the water table. This elevation increases the hydraulic head in the aquifer, thereby facilitating groundwater flow towards discharge points such as the streams or the springs. Now, let us discuss about types of the recharge. First is the diffuse recharge. This is the most general form of recharge. It refers to the precipitation, that is rain or snow melt, that falls fairly evenly or a large area of land infiltrates the soil and moves vertically downward to the water table. It is widespread and occurs over broad recharge areas where the net flow of groundwater is directed away from the water table. In many models, this is calculated using a soil moisture balance technique. Second is the focused recharge. This occurs when water collects in surface depressions or when water flows over impermeable surfaces like clay or solid rocks and is rooted into the permeable zones. Drainage channels or stream beds where it can percolate into the aquifer. For example, in terrain that is hummocky, rain runs off the high points and collects in these hollows like ponds or sloughs. This concentration of water allows it to soak in deep enough to reach the water table, even if the surrounding soil is too dry to allow the diffused recharge. In arid or semi-arid climates, diffusion recharge might be nearly zero because of evaporation. In these places, focused recharge in depressions may be the only way water reaches the aquifer. So this mechanism is notably efficient because the concentrated water can overcome the soil's dryness. It also includes leakage from surface water bodies like lakes and losing streams. Now, the third important recharge is the preferential recharge. This is the shortcut mechanism of recharge. Instead of infiltrating and percolating throughout the unsaturated zone, slowly water rushes down large openings, bypassing the soil sponge entirely. Water travels through preferential pathways such as creeks, fissures, foot root holes or worms burrows. This allows precipitation to reach the water table very rapidly, often before the soil moisture deficit is filled. So this type of recharge is common in fractured rocks. It causes the water table to rise much faster than would be expected if the water had to seep through the soil normally. So this mechanism is sometimes called bypass recharge because it bypasses the conventional soil moisture calculations. Another important recharge mechanism is the mountain recharge or mountain front recharge. In mountain block recharges, in valleys aquifers, water frequently infiltrates the system through fissures, colluviums, and talus in the bedrock of the adjacent mountains, a process known as the mountain block recharge. Surface runoff occurs when water descends from mountainous areas and infiltrates the ground at the interface where the mountains converge with the valley floor. As these streams traverse the permeable alluvial veins located at the basin's periphery, they lose water to the subsurface, thus becoming losing streams. This infiltration predominantly takes place at the proximal end or the uppermost section of the vein, thereby contributing to the aquifer's recharge. We can just see this by an example in desert valleys. Rain may fall on the rocky highlands, enter fractures in a bedrock, and then flows underground directly into the sediments of the valley floor, bypassing the surface entirely. This creates a recharge zone along the mountain slopes while the valley floor remains a discharge zone. Now let us discuss about the groundwater discharge. Discharge refers to the process by which water exits the saturated zone of an aquifer and returns to the surface, the atmosphere or the oceans. Groundwater discharge can be categorized into three primary types: natural discharge to surface water, natural discharge through evaporation or transpiration, and the artificial discharge resulting from human activities. Number first is natural discharge to surface water. Among the various forms of discharge, this one is the most apparent. Groundwater does not remain continued beneath the surface. Instead, gravity propels it towards lower elevation where it meets the land surface. Springs serve as the examples of this kind of groundwater discharge. A spring forms when the water table intersects with the ground, allowing the groundwater to emerge naturally. This phenomena can occur due to the landscape, that is, a dip in the terrain falls below the water table, or geological factors like an impermeable rock layer compels water to come sideways until it surfaces. Discharge can also occur through base flow. Base flow is the specific portion of the stream flow that originates from groundwater discharge. This is the component of the hydrological cycle which prevents the surface water bodies from drying in the absence of the precipitation. So, the natural discharge via evaporation is not always visible as flowing water. In many areas, water leaves the aquifer directly into the atmosphere. For example, phytophyte is a standard term we use for plants that are water loving. These are plants like willows, cottonwoods or mesquite that have their roots deep down, sometimes expanding many meters down to tap directly into the saturated zone. They pump water out of the aquifer and release it into the air through evapotranspiration. In arid regions characterized by a shallow water table, capillary action facilitates the upward movement of water through the soil to the surface, where it is subsequently evaporated by the intense heat of the sun. So, this phenomena is particularly prevalent in desert basins known as playas or the salt flats. So far as the artificial discharge is concerned, anthropogenic activities have increasingly become a significant factor in discharge of groundwater. So, the use of pumping wells exemplifies this, as the drilling of wells and the activation of pumps result in the artificial extraction of water from the aquifers. Additionally, engineered drainage system frequently serves as discharge points. For instance, tunnels constructed through the mountainous regions often intersect with the groundwater, functioning as substantial drainage channel. Similarly, excavations for mining operations or building foundations necessitate dewatering processes which involve the removal of groundwater to maintain dry conditions within the excavation site. Now, we will just discuss how do we measure recharge. Measuring recharge is one of the most difficult tasks in the hydrogeology because they occur underground and out of sight. We often have to estimate them indirectly. We will just discuss some of the important aspects of it. So, the first is the soil moisture balance. This methodology involves a calculation approach where the soil is conceptualized as a storage container. We assess the income, that is the precipitation, and deduct, that is the expenses, runoff and evapotranspiration. It is understood that recharge typically cannot occur until the soil reaches a sufficient moisture level known as the field capacity, allowing water to percolate downwards. By computing the daily balance of precipitation entering the soil against the water exiting through evaporation or plant uptake, we can estimate the residual amount available to the percolation into the aquifer. Lessimeters is another important aspect so far as its calculation is concerned. Lessimeters are enclosed soil blocks, either vegetated or bare, designated to directly measure water recharge into an aquifer. Drainage pipes are installed at a specific depth with the lessimeter to collect water that drains freely from the soil zone, allowing for the direct measurement of the volume exiting the soil. The entire lessimeter block is weighed to determine changes in water storage based on weight fluctuations. Water is extracted from the lessimeter to ensure that the internal water remains at the same elevation as the water table in the adjacent parts of the aquifer. These devices can provide daily recharge estimates. However, the results are specific to the precise locations of the instrument. Field studies have shown that recharge measurements can vary significantly between lessimeters placed only 50 meters apart, while some lessimeters use porous cups and vacuums to extract soil moisture samples for chemical analysis. Those designed for the recharge measurements focus on the physical volume of water moving through the soil column. So far as the water table fluctuation method is concerned, it is employed to estimate the groundwater recharge through field measurements. This method determines the recharge by multiplying the increase in the water table during a recharge season by the specific yield of the aquifer. The specific yield is defined as the volume of water released from the storage per unit surface area of the aquifer per unit decline in the water table, or alternatively the storage capacity available to be filled during recharge. Although this method offers a direct estimate based on empirical data, it is noted to have significant limitations for the method to yield accurate results. Other components of the water balance, such as groundwater flows to rivers, outflows from the catchment, or the abstractions from the boreholes, must be negligible compared to the recharge. Additionally, obtaining realistic estimates of the specific yield necessary for the calculation possesses a challenge. So, tracers are another type of technique which is used to determine recharge by identifying flow paths, quantifying movement rates through the unsaturated zone, and distinguishing between different water sources. The method generally falls into three categories: historical, environmental, and artificial tracers. Tracers are particularly valuable for estimating recharge rates by monitoring their movement through the unsaturated zone. By observing the displacement of tracer alongside changes in the moisture content, hydrogeologists can calculate the rate at which water is moving downwards. Environmental isotopes, which occur naturally in the hydrological cycle, are also used to estimate the age of groundwater and its velocity near recharge areas. Tritium is used to identify modern water that enters the groundwater system after the onset of the atmospheric thermonuclear testing in 1953. Thus, by mapping the distribution of tritium, hydrogeologists can outline the subsurface zone occupied by post-1953 recharge. So, since this zone extends from the recharge areas into the flow systems, the data can be used to estimate the regional variations, linear velocity of the flow near the recharge area, while the primarily used for dating older groundwater carbon, that is C14, help us distinguish zones of water with ages ranging from several thousands to tens of thousands of years, helping to confirm long-term recharge patterns. Stable isotopes, specifically oxygen-18 isotope and deuterium, are non-reactive tracers used to determine the physical sources of recharged water. These isotopes help identify maximum patterns and determining the specific source areas of groundwater. For instance, isotopic signatures, which can be used to link groundwater to specific recharge elevations or climatic conditions. This was all about today's lecture. Hope you have enjoyed it well. Thank you for watching.